Well, we're getting ready to enter a phase in medical neuroscience where we're going to be talking about the senses of sight, sound, and smell. And there's no experience that brings all that together than sitting around a campfire, holding a brain. So I look forward to these next few sessions with you, and if you have an opportunity to be near a campfire over these next couple of days to weeks, you might want to have the experience I'm having right now, where the sense of heat and warmth and the sound of the crackle and the dance of the flame and the smell of the burning wood all brings to mind these incredible feelings of warmth and relaxation and comfort. Quite an amazing bit of neuroscience behind all of that. So look forward to exploring some of these topics with you, and see you next time around the campfire. Welcome again to my home. It's a beautiful day here in central North Carolina, and I'm pleased to begin a series of sessions with you talking to you about the visual system. And our focus today is on the eye. What I have to share with you today pertains to several of our core concepts in the field of neuroscience. We again are confronted with the complexity of the brain as the body's most complex organ. And we again are going to be looking at the structure and function of circuitry that's largely determined by our genes. And these circuits will be foundational for the operations of the visual system in the human brain. And I can hardly think of any topics in the whole domain of sensory neuroscience that has fascinated more human beings over the course of our history than the sense of vision. And so I think when we come to this topic, we certainly are in a position to appreciate how our brain itself gives us this amazing capacity to wonder how vision works. Our learning objectives today begin with the factors and the neural mechanisms that account for focusing an image on the retina. So I want you to be able to describe them. I want you to be able to identify the 5 basic neuronal types that are found in the retina, and I want you to be able to state the roles of each in neural processing. I want you to be able to talk about sensory transduction in the visual system. So I want you to be able to characterize the molecular processes that underlie what we call phototransduction. And lastly, I want you to be able to discuss the responses of retinal ganglion cells to the onset and the offset of light, and the relevance of these receptive fields for the detection of light and shadow. Well, let's begin by looking at the anatomy of the eye. Well, I would just direct your attention to some basic anatomy here. So the eye is comprised of several layers and 2 chambers and some structures that are important for forming the sharply focused image on the back of the retina that are found within the eye itself. So in the anterior side of the eye, we have the cornea. The cornea is a structure that is responsible for actually most of the refraction of light that happens as light passes into the eye. So roughly 80% of the refractive power of the eye comes from the cornea. The remaining 20% comes as light passes through these middle structures near the anterior third of the eye, including an optical lens. And this lens can change shape through a process that we call accommodation. We'll say more about that in just a moment. Well, the space defined by this anterior portion of the eye is called the anterior chamber. And this anterior chamber is filled with a fluid called aqueous humor that aqueous humor is produced by some cells that sit right about in this region here. And that fluid then leaves what we call this posterior chamber between this ciliary muscle and the lens itself. And that fluid then fills up this anterior chamber, and it helps to support the curvature of the cornea. Now that fluid is typically drained by a trabecular network found in this lateral margin of this anterior chamber. Now, should there be a problem with the absorption of this fluid from the anterior chamber, then that can build up pressure within the eye, and that pressure has a way of damaging the peripheral parts of the retina. And as a consequence, in that eye, one might tend to lose peripheral vision. Well, let me try to illustrate the consequences of this, if I may, using a photo from my photo album. This was a memorable trip my family took many years ago. We're in one of the most beautiful sites in all of North America. This is Lake Louise in Alberta, Canada. And if a person viewing my family in this scene had glaucoma, sadly they would not be able to truly appreciate the full majesty of this scene, because their visual field might very well be reduced to just the center of their gaze. Well, let's now turn our attention to the process of focusing the image on the back of the retina. And this is a process that we call accommodation. So accommodation requires the active adjustment of the shape of the lens that sits in the anterior portion of the eye. So here what we see is an illustration of the lens in one of two conditions. In the unaccommodated vision, the lens is relatively flat. So this would be appropriate for far vision. And then over to the right, in the accommodated configuration, notice how the lens is considerably fatter and more round. So this will increase the refractive power of the lens, and this would be appropriate for near vision. Well, how does this work? Well, this is where the active elements of this ciliary body come into play. There is a muscle, the ciliary muscle, that surrounds the lens. And this muscle is attached to the lens through a series of fibrils called zonule fibers. And the way this muscle works and the way it interacts with the lens is really quite ingenious. As this muscle contracts, it makes the aperture smaller that surrounds this lens. And as this muscle contracts, then the tension on these zonule fibers can relax. And consequently, active contraction of the ciliary muscle leads to a rounding up of the lens and an increase in its refractive power. When that muscle relaxes, then it returns to a wider aperture. That causes tension on the zonule fibers. And as a result of that tension, then this lens is pulled more towards a flattened configuration. So one other biomechanical element here that makes all this work is the lens itself. So the lens will tend to ball up into a rounder configuration if it were to be cut free of those zonule fibers. So the elasticity of the lens itself is what gives it the capacity to achieve this more rounded configuration, which is appropriate for near vision. Now, adjustments to the shape of the lens are not the whole story when it comes to accommodation. There's also adjustments to the pupil itself. So the pupil is basically the space created by the iris. So here you notice the iris is a muscular structure that creates this space in the middle. And that is the dark spot that you see when you look deeply into the eyes of another person. Well, of course, what we're looking at is darkness in the interior of the back of the eye. The iris performs this very important function of minimizing optical aberration. Now, the iris also serves to achieve that optimal balance between the amount of light that's necessary to activate the neural elements in the back of the eye called the retina, and overactivating them or bleaching them. So we have an exquisite mechanism that allows inputs from the retina to drive circuitry in the brainstem to constrict that muscle and make moment-to-moment adjustments in the diameter of the pupil. This is called the pupillary light reflex, and we'll spend a bit of time talking about that circuitry in a different tutorial. Well, I think we're ready now to consider those neural elements at the back of the eye, and we will spend much of the rest of the tutorial talking about those elements. What I'm referring to, of course, is the retina. Now, I want to make an important embryological point as we begin to consider the retina, and that is that the retina is really considered to be truly part of the brain. And the reason is that the retina is diencephalic, which is to say, the retina is derived from the developing forebrain, specifically the diencephalon. So as the diencephalon begins to differentiate at the posterior part of the prosencephalon, something called the optic vesicle forms. And this is an outward pouch that we see from the lateral margins of the diencephalon. And this pouch grows out to meet other tissues that together form the eye. The retina and an important layer of tissue just behind it called the pigmented epithelium are derived from this diencephalic tissue. So one might wonder, why then do we call the optic nerve if it's really an extension of the brain? Well, I think that's a legitimate question. But the important point I want you to take away here is that the retina provides us with a unique opportunity to look into the eye of a patient and actually see tissue derived from the brain. And that gives us an opportunity to examine that tissue as well as the vascular supply to it and perhaps gain some insight as to the status of what's going on deeper in the cranium. All right, well, let's look now at the retina itself. And as I mentioned, there are two kinds of tissues here that are derived from this optic cup that constitute the retina. Right at the back of the eye is a tissue called the pigmented epithelium. This is a very dark tissue because of the presence of a pigment, and I'll talk more about that particular layer of cells in just a moment. The rest of this is what we call the neural retina, and it's comprised of 5 basic types of cells. And I want you to notice something about the organization of those cells relative to the eye itself. So the back of the eye is out here somewhere. Okay, so the pigmented epithelium is against the inner surface of the sclera, which is what we call the white part of the eyeball that we see from the outside. And in order for light to activate the cells that do the job of phototransduction, it has to pass through this entire neural retina, because the phototransduction process is out here, right up against the pigmented epithelium. So this is where phototransduction happens. And that may seem somewhat surprising, that light would have to pass through this tissue before striking the photopigments that transduce that energy and generate an electrical signal. But we think this is the way it is for a very important reason, and it has to do with the relationship between these photoreceptors and this pigmented epithelium. So if we look more closely at that relationship, what we discover is that the outer tips of our photoreceptors make intimate contact with this pigmented epithelium. And that's critical for the function of the pigmented epithelium in the whole process of keeping these photoreceptors competent to transduce photon energy into neural signals. The pigmented epithelium is involved in recycling the discs of membrane that contain the photopigments. And we know that from experiments that allow us to trace the movement of discs from a more proximal position to a more distal position. And what we find is that eventually the discs are completely engulfed by this pigmented epithelium. And that's important in recycling the photopigment that's otherwise bleached by the interaction with photons. So this raises a rather serious problem that can happen with trauma, and that is what can happen when the photoreceptors are detached from this pigmented epithelium. So this can happen with a sharp blow to the head. It's a particular problem in people who are in sports that are subject to a blow to the head, and it's certainly something that can happen with a motor vehicle accident or some other trauma to the head. So retinal detachment prevents this intimate relationship between pigmented epithelium and photoreceptor, and as a result the photoreceptor no longer has a chance to renew the photopigment and recycle its disc membrane. So now let's consider the rest of the cells that comprise the neural retina.